right, so we are going to start talking about exponential functions today, and this first lesson is an introduction, and we'll talk about, you know, what it means for something to be an exponential function and all of that stuff. So first and foremost, exponential functions are power functions. Okay, so they're power functions, and the difference here is that, whereas before we're used to seeing something like y equals, you know, x squared, x to the 5, and so on. Now exponential functions have their base as a constant and the exponent is the variable. So for example, now an exponential function will look like y equals not x squared, but 2 to the power of x. Okay? So some examples of exponential functions are listed below here. Like you have f of x equals 3 to the x, f of x equals 1/2 to the x, f of x equals e to the x minus 1. Those are all exponential functions because you have a constant to the power of a variable. Okay? Now, let's talk about where, you know, one situation where exponential functions apply. So suppose you get to school on a Monday morning, right? And it's, you know, you haven't seen your friend for like a whole 48 hours, and you're like, oh my God, I haven't seen you like forever, and like you give them a hug. And as you're going in for the hug, your friend, you realize, is not feeling well, and they're coughing and sneezing, and they cough and they sneeze, and here we go, we're now hugging. And so what happens is some of the bacteria from their body now lands on your body. And whereas you are feeling totally fine, you had practically none of that bacteria in your body. All of a sudden, like right around bonus, okay, you're not feeling so well, lunchtime, you got a headache, you feel kind of faint. You go home and then you're in for it, like you're done. You're in bed, you got a fever, you're, you know, all of that. So what happened? In the morning, you were feeling perfectly fine. A couple of, you know, like just a few bacteria landed on your body, and within just a few hours, in a very short amount of time, all of a sudden they increased by the millions. And now you're completely sick. So that's the biggest characteristic of exponential functions. In a very small amount of time, there is a huge, huge, huge increase. All right? So then you go to the doctor. They take one look at you and they're like, yep, antibiotics. And then as soon as you start taking the antibiotics, as quickly as you started, you know, having symptoms, you now start to feel better. All right? So what happened? In the first case, there was an exponential increase, a growth. And then in the second case, there was an exponential decay. So let's take a look at some examples of how these graphs look. All right. In the first case, take a look at this one. This graph here is one of exponential growth. So look at this. Look at this characteristic. Here, so suppose this is like the bacteria growing in your body. This is like 8 a.m. And then, you know, just a tiny little bit of time later, okay, only a small amount of time has passed, but look at how much more bacteria there is now. Do you see how much has increased in just a very small amount of time? That's exponential growth. All right? Okay, so now, can you say that initially, like, you had 0 bacteria in your body? Is that possible, to have 0 bacteria in your body? No, you had very, very little. You had a number comparable to 0, but you never had 0. So how much bacteria you have in your body can never hit 0. That means an exponential function should always have a horizontal asymptote. Now, here's the biggie. For the default case, and for the first ones that we're going to do, it's all the default case. For the default case, the horizontal asymptote, there is no calculation. It's always y equals 0. That you have to know like you know your name. Okay? Another general fact. The domain for all exponential functions is all real numbers. Okay? Now, the range, so these two here, horizontal asymptote domain, like they're free points. The range is always y is either greater than what the asymptote is, or y is less than what the asymptote is. Alright? So if you said the horizontal asymptote is y equals 0, then this is either going to be y is greater than 0 or y is less than 0. And we'll figure out how to do that. If it sits above the asymptote, greater than 0. Okay, look at this next example. This is one of exponential decay. You had a whole bunch of bacteria, and now you are, they're decaying, and you almost have 0 bacteria. So, and it's the same things that apply. Horizontal asymptote is always 0. Domain is all reals, and we do the range in the same way. Okay, now, if you have a graph, how to tell if it's growth or decay, right? So look at what happens here. As you move to the right, don't look at if the graph is going up or down. Think of it as the graph moves away from the x-axis. Okay, so this is as you go from left to right. As you go left to right. Okay, here, look at the second one, that's decay. As you read left to right, right, the graph moves towards the x-axis. Okay? All right. So now, take a look at this. Well, look at this one. Is this an example of growth or decay? Growth. What about this one? Growth, or it's either one or the other. How did we define it? Moving away from the x-axis, it's growth. All right? So look, this is decay. And then this is also decay. All right? So look at these two examples. Huh? Well, yeah, so look at this. Think of this as like the national, right? At some point, let's say a country owed like $3 billion. That's how much they're in the red. That's how much they're in the negatives, $3 billion. Then the economy gets bad, and then now they owe $50 billion, and then $1 trillion. So the debt is exponentially growing.
What about if it was above the x-axis? Right now it's below it.
Well, it's below because you owe money, right? Like if it changes course and goes back above, then it's no longer an exponential function.
So what if it starts above the x-axis and then crosses it down?
It could do that. Like it could start above and go down. Yeah.
So that would be like gaining money growth.
This one?
Yeah.
This is when like you have a business and like the first month you make $100,000, the second month you make $1 million, the third month you make $1 billion. That's what it is.
But in that graph, it's like the debt is growing.
This is the debt growing. How much you're in the red is growing. And then here, suppose a country was doing really poorly. They owed $12 trillion. And then the economy starts doing much better, and now they only owe $1 million. So their deficit decayed. Okay? All right. So that's how you tell if something is growth or decay on a graph. But how about given a function? So if you have the function, in order to tell if something is growth or decay, you have to look at this value b. Okay, so what is b? The general form of an exponential function is y equals a b to the x. That x, the exponent, belongs to the b, right? So what you have to do is you have to look at the equation. You have to single out the number that is being raised to the exponent. And if that number is greater than 1, then it's exponential growth. So if the number being raised to the exponent is greater than 1. If that number b is between 0 and 1, it's exponential decay. So look at this one. What's being raised to the power? 1/2. 1/2 is between 0 and 1, so it's decay. So we don't look at negatives. You just look at the absolute value of the number. All right, so let's classify some of these. What's the first one? Growth or decay? Growth. Next one? Decay. Next one, C?
Oh, wait,
Decay. And D? Growth or decay? What's being raised to the exponent? 1/4 is what's being raised to the exponent. That's less than 1, or between 0 and 1, so it's decay. You ignore the number in front. It's just the 1/4. Now, if there were negatives in front of these, nothing would change. It would still be the same. Okay? All right, let's graph one of these. 2 to the x. All right, so first, asymptote, we said the default case, it's y equals 0. Y-intercept, that's when x is 0. So you say y equals 2 to the 0. That's 1, 0, comma 1. No, it's every time you have to do x equals 0. That's what's constant. That's the y-intercept. The y-intercept happens, to find the y-intercept, you make x 0. Okay? That's in any situation. So now, okay, so 2 to the x is growth. Now I need to graph this, right? First I put in the horizontal asymptote. And now, in order to graph, I need to make a table and pick points. So you need to pick points for x. Obviously, you can pick whatever x values you want. However, with exponential functions, numbers get very fast very quickly. I mean, very big very quickly. As a rule of thumb, my preferred set of values when it's growth, it's these, -1, 0, 1, 2. Okay, so these are good for growth. Is it set in stone? Like, is it the law of the land that you must pick these points? No. Sometimes, is this not a good choice? Yes. But for most of the cases, this is a pretty good start. Okay, now you're going to plug it in. So look, we're going to have 2 to the -1. And what happens when you have an exponent that's negative? You take the reciprocal, 1/2 to the 1, so that's 1/2. Okay? Next, 2 to the 0, 1. 2 to the 1, 2. 2 to the 2, 4. Okay? And then at -1, you have a 1/2. 0 is a 1. At 1, you have a 2. 2, you have a 4. And that's how you graph it. Oh, you know what? Let me tell you this. You have the 4 points, right? So if you do this, there is no credit. Because this isn't connect the dots. We're over that. This is an exponential function, and in the very beginning I told you 2 things about an exponential function. 1, that it increases rapidly, so you have to show me that. And 2, that it has a horizontal asymptote, and it gets very, very close to 0 but never touches it. So you have to show me those 2 ends. Okay, these are the freebies now. Domain is always all reals. The range, you put a y. Look at the asymptote. It's at 0, so 0 here. The graph sits above the asymptote, so it's greater than. Also, you can look at the function. If it's a positive 2 to the x, then it's greater than 0. Otherwise, it would have been less than 0. Okay? All right, let's do another one. What is this one, growth or decay? Decay, but the asymptote is still y equals 0. The y-intercept is 1 over 3 to the 0, 1. Now, for decay, I go to the left one. I start at -2 and I go to 1. Okay, again, just because most of the time, good. So these are good for decay. Okay, so here I have 1 over 3 to the power of -2. The negative makes it a reciprocal, so 3 to the 2, 9. 1 over 3 to the -1. 3 to the +1, 3. 1 over 3 to the 0, 1. 1 over 3 to the 1, 1/3. Okay, what's the domain here before I graph? All real numbers. What about the range? I have a y, I have a 0, greater than or less than? Greater because it's a positive, okay? All right, so let's see if that will come out in the graph as well. Asymptote first. Again, drawing an exponential function without the asymptote is like drawing a little bunny without the ears. Okay? It's just a circle with a happy face inside. Okay? All right. So, at -2, y is 9. At -1, it's all the way down to 3. Then 1. Then 1/3. And look at that cute little decay equation. Isn't that cute? Mm-hmm. All right. So now, look at this next one. I think there's supposed to be parentheses around this, right? Okay. So look. Is this growth or decay? Decay. All right. What's the asymptote? Y equals 0. For now, until I tell you when it changes. Y-intercept, -0.5 to the 0, -1. Before I do the table, I want to do domain and range. What's domain? Range. Y less than 0 because of that negative. Okay? Cool. Asymptote. Since it's decay, I've picked my points. All right, let's take a look here. I have -0.5 to the power of -2. Oh my gosh, how much is that? Can we do that by hand?
Yes.
So that's -0.5 to the power of -2. What's 0.5? That's 1/2. So is that like -2 to the 2? Is that -4? Negative or positive? What do you think? Okay, who does the exponent belong to? The 2, the negative, or both? Just the 2. It would belong to both if it was like this. If it was like that, it would belong to both. Okay? So that's -4. Okay. Go ahead and take out your calculators for a minute and plug in the same one into your calculator. Here you can put this stuff in correctly, right? So it's negative 0.5 to the power of negative 2. Okay? So that's negative 4. And what do we get when we put in negative 1 for x? How much? Negative 2. And then negative 0.5 to the 0 is negative 1. Negative 0.5 to the 1 is negative 0.5. Okay, so let's graph. We get negative 4, negative 2, negative 1, negative a half. Okay? All right. Did that graph confirm what we said about the range? Does it sit below the y-axis, the horizontal asymptote?
Yeah.
It does, yes.
Can I put arrows at the end?
You don't have, it's up to you.
Instead of like drawing, like,
Oh no, you still have to extend it.
but like,
You-
extend it all the way to the end of the graph, or like extend it a little and just draw an arrow. Like, would that be fine?
Extend it so that like there's no ambiguity that you know that it extends, you know? Okay, so here, let's do this next one. Asymptote, still y equals 0. Okay? Y-intercept, 3 times 2 to the 0. 3 times 1 is 3, so it's at 0, comma 3. So that's y equals. Growth or decay for this one?
This.
Growth. So here's my table. All right, so here I have 3 times 2 to the minus 1. This is 3 times 1 over 2, 3 over 2. So that's 1.5, right, when we need to graph? Okay, 3 times 2 to the 0 is 3 times 1, which is 3. 3 times 2 to the 1, 6. 3 times 2 squared, 12. Okay, let's put in the asymptote. Okay, now look, at negative 1, I'm at 1.5. And then 3. And then 6. Okay, now look, I have 3 points. My fourth one is going to go above the grid. So it's okay to be satisfied with this and then just graph it with the 3 points. If you didn't have 3 points, you would have had to pick another one, right? Okay, domain is all reals, and range is y is greater than 0. All right. This one, what's the asymptote? Y equals 0. Intercept, y is negative 3, 3 to the 0, negative 3. Domain, all reals. Range, y is greater than 0. Is that right? Is it greater than 0? No, it's less than 0. How do we know that it's less than 0? Because of this negative here. Okay, so for a range, you look at the sign, plus minus, of here. If it's positive, it's y is greater than. If it's negative, it's y is less than. Okay? The other one is growth and decay, and that doesn't have anything to do with the range. Okay, so now I'm going to give you about 2 minutes to plug in the points and to graph this one. Okay, when you're done, go ahead and graph. Okay, so this one, what values did you get for the table?
-3, -9, -27.
Right, and when you plot the first three, the last one is, it's too low, so you don't need it, right? So 3 is good enough, and you can just graph with the 3. Okay? All right. Next one. Take a look at this now. In this example, I have f of x equal to 5 to the power of x minus 2, right? The exponent has been changed. So there is an addition or a subtraction from the exponent, right? Because the minus 2 is made to the x, this is a horizontal shift in the graph, right? So, does this move to the left or to the right?
Right.
To the right. Okay, so after change is made to the x, you go in the opposite direction of the sign, right? Why? Because technically in the background, it's x minus 2 equals 0, x equals plus 2. So this graph has been shifted to the right by 2 units. Now, if it's shifted to the right or to the left, the horizontal asymptote doesn't go anywhere. It's still there. So the asymptote is still y equals 0. But now, the y-intercept, it's going to be y equals 5 to the negative 0 minus 2, 5 to the negative 2, that's 1 over 5 squared, 1 over 25. That's a tiny little number. Okay? All right. So now, take a look at this one. This is growth, so instinctively I picked these same points. But now, here I go 5 to the power of minus 1 minus 2, 5 to the negative 3, 1 over 5 cubed, that's 1 over 125, right? Okay, that's not a graphable point. Okay, what about the next one? 5 to the 0 minus 2. I just did it up in the y-intercept, right? That's 1 over 25. 5 to the 1 minus 2. 5 to the negative 1. 1/5. Okay? Those are still tiny little numbers. Okay, 5 to the 2 minus 2. 5 to the 0, 1. Okay, so look. My y-intercept, I'm sorry, the horizontal asymptote was this. Okay? So 1 over 125, 1 over 25, these are too tiny to be able to graph. Okay, I can manage 1/5, right? I can manage 1/5 when x is 1. I can manage x is 2, y is 1. And now I have 2 graphable points. So guess what I do? Add a third. Add x equals 3. So now I have 5 to the 3 minus 2 is 5. So I graph these 3. Now, oops, that's a 5. Okay, so look, if on the test you have the foresight to already know that these are too tiny and you just picked like 1 and up, that's totally cool with me. Okay, so that's what that looks like. Alright, domain is all reals. So you don't really see the shift because it has similar form. So like the whole thing should have moved like over. Okay. Look at this next one. Now I have 1 over
Wait, what
3.
was the range was
Y is greater than 0. Now I have 1 over 3 to the x minus 3. Right?
It moves
No. This minus 3,
right.
Up. Down.
this minus 3 up here is happening to the y. So this is a vertical shift. Right? So the graph shifts down by 3 units. Now, if you, because it's not in the exponent. Now, graph and asymptote are connected to each other. You can't move one up and one down, okay, without the other one. So, when the graph moves down 3, the asymptote also moves down 3. So now instead of y equals 0, it's y equals negative 3. So, the asymptote is always going to be y equals that number, negative 3. Okay, so there's zero thinking involved. Well, minimal thinking involved. Okay? Free points for this stuff. The y-intercept, y equals 1/3 to the 0 minus 3, negative 2. Okay? Alright, so here, we're going to have 1 over 3 to the negative 2 minus 3. What's 1 over 3 to the negative 2? 9 minus 3? 6. Hang on for a second. I'll have you guys work with the calculator first. So 1 over 3 to the negative 1. So that's 0. 1 over 3 minus 3. That was negative 2. 1 over 3 to the 1 minus 3. It's 1/3 minus 3. How much? Negative 2 and 2/3. Which is negative 8 over 3. Okay, domain is all reals. Ranges. Y is greater than 0. Okay, asymptote this time is where? Negative 3. Okay? And now look. At negative 2, we're at 6. Then 0. Then negative 2. Then negative 2 and 2/3. That's how it looks. Okay, now. Again, make it go all the way down to the asymptote, or close to the asymptote. Okay, right now, go ahead and take out your calculators again. And we're going to graph this function right here. So go ahead and take out your calculator into the calculator mode. Give me a second and then I'll let you go. Okay. So go ahead and plug this function in. So in parentheses, 1 over 3 to the power of x. Whoops.
Wait, how come the range is y?
Y is great. I'm sorry. I'm so sorry. I'm so sorry. What should it be? Nope. It's greater than negative 3. Sorry about that. So 1 over 3 to the x minus 3, right? Okay. And look at what you have. Okay. So now, you should be able to extract points on this graph, like using the calculator, because for the next lesson, you can't do it by hand. So here, we're going to go to menu. If you can do the table, do the table. Some people don't like the table because it's like too tiny of a screen. But basically that's what the table looks like, and then you could just go x equals 1, x equals 2, x equals 3, and so on. Or, look at what else you can do. Menu, table, remove. You can go to menu, analyze graph. I'm sorry, not analyze graph. Trace, graph trace, and look. At x equals 0, y is -2. So now, I want x equals -2, right? So just type in -2, enter, and it's 6. -1, enter, and it's 0, and so on. Okay? So that's how you can do it on the calculator portions. Questions? Okay.